Good morning, guys. Welcome to another episode of Xa Talk Show. Today is November 15th, Friday, 10 o'clock in the morning, San Francisco time. Now, YouTube says, warning, please check the video resolution. The current resolution is 1920 times 1080, which is not optimal. What? Not optimal. Very annoying. Not optimal. Well, so good morning, good morning, people. Emily, Allen, Fitch, Bart, Nebo, and Sintu. So today we are going to do JavaScript, the wonderland of JavaScript and mathematics, fantastic mathematics. Good morning, Kathy. And have a look at the math. Now this is math in Second Life, and that is what we're going to do. Polyhedra, platonic solids. Wait, do I look good? Check. Okay, I look good. I look good. I'm beautiful. So today, math, platonic solids, regular polyhedron. Now this is called equal angular spiral or logarithmic spiral. And that I don't know what I forgot what is that. But and this is a bundle. This is Hopf bundle. Very advanced topic in differential geometry and differential geometry. Hopf bundle, and you have this Japanese girl in kimono, and you have this fantastic thing, and you have this trifoil knot and Mobius strip, and you have this Japanese girl, Eureka 7. So you guys, do you guys know what character this is? This is Second Life, so it's fantastic. This is almost 10 years ago, 2008 also, and this is one of the most wonderful experience in Second Life. As I mentioned before, in Second Life, everything is built by yourself, by the players. So you go there, you build these things. So this dome, this is called this dome is called geodesic dome, which is a idiotic name. Okay, but people call it that because of the Buckminster crackpot. There is this guy, semi-mathematician, whose name is Buckminster. How do you say his name? Math, yes, JavaScript. So there's this guy, Buckminster, guy. Okay, let's look up them. Buckminster. So Buckyball. I remember I know how to find his name by just searching Buckyball. Okay, this guy, in my opinion, is one of the crackpot. So we are going to do some prelude, then we are going to get on into JavaScript. We are going to code live three-dimensional rotation of a cube in real time, and it's gonna need to be less than 1 hour, and no libraries, no framework, no nothing, pure JavaScript, and it's going to be within 100 lines. Yes, Buckminster Fuller, that guy, is a crackpot. He's one of the crackpot to me. Okay, so what's his name? So let's go. Well, there it is. His name is there. So that's etymology. Okay, yeah. Is this guy? No, that's not them. So preparation and occurrence, etymology. Let's go find his name. This guy. So how do you say it? Fuller, L-E-R. Oh, the Wikipedia doesn't link to his name. Amazing. So Buckmi. Okay. This crackpot. Oh, okay. It's quite interesting. His name is not mentioned in the article's content. Wait, let's see. Let's try it again. uh, well, anyway, so let's just go back here. We found this guy thinking out loud. This guy, okay, this is a crackpot. Now, anyway, he did quite a few things. He's kind of like the code leader kind of thing, code in technology and sciences, a code kind of guy. So he created, well, he pushed for these code kind of people. They have a bunch of jargons always come with code. Okay, so he has this spaceship Earth Dymaxion, this ephemeralization, synergy, tensegrity. All these are crap. Fuck this fuckhead. So he created lots of these things. So one of the things he created is called geodesic dome. Okay, Xali geodesic dome. Mensa. By the way, guys, I'm a member of Mensa. Okay, it is true. I'm a member of Mensa in 1993 or so. You see, it requires membership. It requires payment to be a member. So in 1993, it's like $40 or $50 a year. So I was a member of Mensa. Geodesic domes. Okay, let me show you this fascinating Paul Erdos. He had his own words too. I don't like the Paul Erdos guy, but Paul Erdos, he's a mathematician, qualified mathematician. So I don't like Paul Erdos, and in physics, there is this guy Feynman. Like every programmers, every minute, every hour, every day is that Feynman. This Feynman thinks Feynman is that idiot. I don't like these people. Okay, Feynman, Paul Erdo, but these two person, they are solid. Okay, I just don't like them. Their personality, their style, I don't like them. But however, this guy Buckminster Fuller, I think he's a crackpot. Okay. Uh, anyway, that's not paying membership. Maybe 15 years ago. Oh, Nabi Young. 15 years ago. Wait, aren't you the game? You work in a game company, right? But anyway, so here we got. I have a collection of the most beautiful things. Geodesic dome. Now, okay, so the reason we mentioned this because we were looking at geodesic domes, and I was saying this is a stupid name. Okay, it's an idiotic name. It doesn't. It's well, I'm not going to talk about the history of that word, but anyway, it's a stupid name. The proper name for this kind of thing should be regular polyhedron dome. Okay, or you just call it polyhedron dome. Okay, or spherical dome. Okay, not geodesic because it's nothing about geodesic. It is idiotic. Okay, that book, Fullminster guy, crackpot. And by the way, Emily, good morning, Emily. Emily, have you been to this place? This is a beautiful place. The Eden Project. The other day you went south. So I was going to ask you about whether you've been to this place. This place, um, it's in UK, United Kingdom, Cornwall, Cornwall, Saint Austell, Cornwall, UK. Okay, so there it is. You have geodesic domes, and you have this dome in Montreal. I was there like 30 years ago in 1987 or so. You have not been there. Oh, okay. So it might be a a place to visit. Uh, and then you have the Disney Space Earth. and stuff like that. So we are talking about domes, and all these are beautiful, uh, modern architectures, so-called domes and domes and domes and domes and domes and domes and domes. And you have igloo hotel. This is a primitive dome. Uh, Technically, I don't think. Well, they are all this kind of architecture. They are all called domes. Okay, but this is not. This one is not. Apparently, it's not spherical. Okay, so and this one is atomium. Now this one is at one of you people's place, Belgium. Okay, so you guys can visit this atomium. It's modeled. It's modeled on the molecular structure of iron, I think. Okay, I forgot the details, but you got this thing. Okay, so we gonna do JavaScript. Yes, I guess. Yeah. Okay, no problem. No problemo. Let's see. There's a forum for this stream. Yes. Okay. So we're talking about geodesic domes. So now let's get back to So I was talking about Second Life. So this mathematician Henry Sedgman, he introduced me to Second Life. And there it is, tetrahedron. No, this is octahedron. So you have this octahedron, a stack of octahedrons. And then I want to show you this. This is built by my girlfriend. Okay. Lorentz attractor. I had the most wonderful time in Second Life when we are doing this. So what happens, so Second Life is like a 3D game, right? So this character in the middle, like floating in the sky, that's me. So you see these stars, they are like they are called sprites. They are actually called particles. So this shape is generated by particles, basically just like images. So anyway, these are generated in real time, and you can look around and you can follow it. It's quite amazing. It's quite amazing to experience this thing in real life. And we have quite a few things. We're gonna talk for hours if we're gonna talk about this. Let's see. Let's open some of the pages and let's just see what they are. So this Lorentz attractor, that's amazing. Let's see. Okay, and then you have Alexander's horned sphere. This thing. Now this thing is nesting forever. You see this ring has a little ring at the end, and that little ring has a little ring in the end, and go on forever. They interlock. So this is a monster in topology. This thing, this shape is created. This concept, this object is a monstrosity in topology. And then you have these Spaninsky's triangles, and that is me. Okay, I'm a trans. Okay, back then you don't have the trans word, not really, but I was dressed as a girl in Second Life. And this woman, this lady, Bath Bathsheba Dawn, she is a mathematician. She is a great artist, mathematician artist. Now you might have heard of her or seen her things if you are into math. Just search for her name, Bathsheba Dawn. Anyway, it's amazing. Okay, Second Life. So you have iterated function systems. You have this inversion kind of turning a torus inside out. Okay, so we got lots of things. Okay, then this is the most beautiful thing in Second Life. Then there we have a icosahedron in this dome, and these are beautiful artistic Japanese comics, and there's this Neko, which is my companion in Second Life, and this cat is me, and there it is. There we are, and it's truly amazing Second Life. And you have other things. So Second Life, that was then. I haven't been to Second Life for like 7 years or so. So we're gonna do JavaScript. Yes. Let's see what some comments. Guy in real life. You are a girl equals to guy in real life. That's not true. Actually, today there's even 10 years ago. Okay, that's another topic. Anyways, it's because I can talk about that topic about girl game players, female presence online. I can talk about that for 20 minutes. But let's do that next time. Bathsheba is from the Bible. She's a woman. She's a woman King David cheated with. Oh, I didn't know. Okay, that's interesting. Interesting story. So we're gonna start JavaScript. Okay, don't worry about that. And since we are talking about polyhedron, guys, I have a collection of great software for fun software for polyhedra. I highly recommend this one by Jeff Weeks. You just go there and download. Okay, go to my website. You go to Xali. Actually, just search for Xali polyhedron. You'll find it. Okay. And okay, let me. Why don't I just paste the link? Cut and go to. It has developed significantly. You mean the Second Life? Okay, that's interesting. So what are other comments? Let me see. So you go to this page. Okay, the first one is fantastic. Download it. It's free on Windows, Mac, um, or iPhone, or even iPhone. So it's very fun. And you can learn something about polyhedra, the math of polyhedra. Then you have other software for doing polyhedra. And the magic polyhedrons are one of my favorite math puzzles. This is my piano, by the way, back in year 2000 when I had money. When I had. Okay, so anyway, polyhedron, and let's do JavaScript then. So let's see what the comments. Okay, that was not frozen for me. Comments. Okay, comments. Keep the comments going like a river. The spice must flow. Okay, so Serpinski. Okay, that's how you pronounce it, I suppose. Developed. Xartalk ML. Okay, that's Bart's forum. Replace the underscore with a dot. Okay, so let's do the JavaScript. So we're gonna do it from scratch. And first of all, of course, I need to show you what it looks like. Very simple. Okay. Now you don't need to know a lot math. You don't need to know any math. Okay, I'm just gonna show you how to do it from scratch. So here it is. We're gonna write this. You can rotate it in real time. You can change to octahedron, rotate in real time, and that's what we're gonna do. Okay, let's begin. So at the beginning, we're gonna create a HTML file. Okay, save this as HTML. Okay, let's say xxpoly poly.html. Okay, magnify, and let me start command log mod. So for you Emacs users, you can see all my Emacs commands on the left window. Okay, so HTML start a kind of a HTML skeleton, rotate cube. That's what we're gonna write. I'm just going to show the most basics. Once I'm going to show you the core techniques. Then you can create any other polyhedra. Okay, save it, create a new file, name it JavaScript. So we're gonna paste it, linkify it. Okay, so this is our JavaScript file. Open it. Wait, open it. Yes. Okay, here's the file. Comment today's date, and now close that. Save. Show in browser. There's nothing. We're gonna show this in Chrome. Okay, so let's go to Chrome. Actually, so this is our file. Okay, so let's put a header. H1 rotate cube. There it is. Okay, now go back to here. I need to copy this to my Excel talk show so we have a memory of what we talked about. So okay, this crackpot. Okay, close. I don't want to close that. Okay, let's go to chat. Okay, so let's do. So now we got the template. Now first of all, we need to create a div, because that's where we're gonna insert our graphics. Okay, now poly anchor. Okay, usually they call this anchor. So I think, do we have JavaScript coder here? Raise your hand, please. Do we have anyone who code JavaScript here? I know Alan does. So in general, how do you call? Just registered for the forum. Okay, so poly. Poly. So what we gonna do? So we're gonna do let's say polybox. Okay. Let's say draw area. I'm confused about every time there's a naming. I get confused because you have to go back and forth about what is a better name. Okay, so anyway, so we have a div draw area, and we need that because then we gonna insert graphics there. So here is our JavaScript code. Let's constant. Okay, constant draw area equals to document get element by ID. Okay, draw area. So that gets the element. Okay, now what we need to do next. Okay, I need to make my font larger. Okay, settings. Okay, hold on a second. So settings, font size. Okay, default font. Let me make my Emacs font larger. So Menlo 15. Okay, Menlo 15. Okay, let's see. Okay, so we are back here. So what is it we want to do now? We want to Emacs settings close. Okay, so we got that. The next thing, so we're going to begin by drawing one surface of a cube. Okay, here's what we're going to do. Write a app that does rotate a cube in real time. So first of all we're going to start to do is just to have one face of a cube and trying to rotate it. Okay, so let's define face. constant. Okay, face. We need 4 coordinates. So face is coordinates. Okay, so 4 points in 3 space in 3D. So the points, the coordinate will be, let's say it will be 1 1 1. Okay, 1 1 1. Okay, let's copy that. Then let's go back here. Then 1 negative 1 1. Okay, then go down. You can figure this coordinate out. So then go down, it'll be 1 negative 1 negative 1. Then go back there, it'll be 1 1 negative 1 1 1 negative 1. Check. Is that correct? I think that's correct. So we got a face of a let's say face 1 of a cube. Now we got a face. We have to now create a, that's a coordinate of a face. Now we need a projection. Now what projection does is that it will take a 3D point and put it into a 2D plane. So project. So we're gonna write this function, okay? Parallel project, constant arrow function. Parallel project, it takes a 3D point, x, y, z, and it returns a 2D point. In this case, we simply drop the z coordinate, okay? So that's a projection. Because your screen is flat, it's 2D, so you want to any 3D point, you drop the z and then you can draw it on your canvas. Okay, then we're going to create a SVG. Okay, so I'm going to show you my SVG tutorial, so you can go to and you can read about the SVG things. Let's go here. So SVG tutorial. This is important because without this you cannot do it. Let's get back to the talk show and put it here. Okay, so back to close that. Back to okay. So what are we gonna do? We're gonna first of all we are going to create a SVG element like that. Okay, so to do this in JavaScript, so we are using JavaScript to create these elements. So how do you do that? You go to SVG, you call this function. Okay, so let's just do it. SVG element. Okay, SVG element, you say document create element. Okay, ng, because that's what you need. Let's double check. So you go to SVG, you go down, there is a scripting SVG, and here is the function you need. Create element ns, not ng. Ns stand for namespace. Doesn't matter if you don't know what it means, because that's a complexity created in XML. So anyway, so you call this function create element ns, then that will return a SVG element. It will basically return something like that. So now you want to add, okay, so add the width and height. Okay, Okay, so add attribute, add attribute, set attribute, set attribute. Okay, that's what you want. So set attribute with, let's say 500. Okay, then height. Okay, then we have that. Okay, and then we want to attach our SVG element to the draw areas, to the div. Okay, to the div element on the HTML page. So what you do is speech permitted. What do you mean? So what you do is we want to append child. Okay, that's what you want to do. So SVG element dot append child. Okay, and append the draw area. So you go back to our page. Okay, then you press Command Option I to turn on the JavaScript console. Now on Windows it's Control Shift I think, or Control I think it's Control Shift I, but you can find out, or press F12. So then you go to Elements. Then you can see here we have created. Oh, we have not created. Did we create? So let's see. We have the SVG. Oh, we got this wrong. So this should be draw areas, attach SVG to it. Okay, this is the right way. So go back to the browser, refresh. Wait, what? Oh, it's not there because we got it wrong. It's not class, it should be ID. So let's go back to our HTML page. So instead of a class, it should be ID. Okay, now refresh in browser. Why don't we see SVG tag here? Because the code is wrong. So why don't we? So draw area is the div. Okay, and draw area. Okay, box one. Okay, let's just name box one. So I keep renaming this thing. Annoying. Box one. Okay, box one is the place we want to draw. So box one. Then we box one append child SVGEL. Why is it not working then? So let's refresh. Oh, because I have JavaScript off. What an idiot. In Brave, okay, you cannot turn. Okay, so let's go back to Chrome. Then let's do it here. Okay, how long I've been talking? 33 minutes. We gotta go faster. We cannot finish this. So there we have it. You can see we have added, a SVG tag there. That's how you do it. Now we are going to create this face in SVG. So we're gonna, just like before, we copy this line, paste it here. We're gonna SVG face one. Okay, so here's the SVG, and the tag we want to use is polygon, Polygon. Okay, and what are the attribute? The attribute are, so let's go back to SVG and our SVG reference polygon. There it is. So here is the syntax. So let's copy it. So we want to create something like that. Okay, this polygon. So points is the thing. So points, and the point should be like that. So we need to generate that. Okay, so how do you generate? So we need now, so you see Now what we need to do, so we got 4 points in space, in 3D space. We want to project them to the plane, drop the last element. So we got a bunch of two-dimensional points. Then we got 4 of them, 4 two-dimensional points. Then we're gonna change the array into this string format. So how do you do that? Easy. Okay, so let's do that. So phase1 dot map. Okay, we apply a function parallel project, so that will return a list of two-dimensional points. Each element is just x and y. Okay, now once we got that, we just say toString. Okay, then it will become like that, a sequence of numbers, a string. And okay, so this is actually what we want, so we put it there. Let's shrink this thing, okay, so we are trying to create that, so let's do that. So another thing we need is this. Okay, we need to add a style, otherwise it won't have any color and stuff sometimes, because in SVG sometimes the default style is blank or none. So stroke blue, fill yellow. Okay, let's try that. So once we have, wait, this should be called SVG face. So this face will be something looks like that. Actually, it'll be a square. Okay. So once we got the face, we need to attach it to the SVG element, basically nested inside the SVG element. So let's just copy the code. Let's do it. So basically like that. Okay. So SVG element, append child, append the face, then you append the SVG to the box. Okay, let's go to the browser, refresh, let's see what we got. No, we failed. We have failed. So box ID equals to box1. Then how come we don't see SVG inside? So box1, what's going on? Refresh. And is there any error messages? Let's go to console. Console, syntax error, missing a parenthesis. What? Line 21. Okay, I'm missing a parenthesis, it says. Yeah, indeed. Because extra comma, because extra semicolon. Semicolon is a pain in the ass in JavaScript. Refresh. Huh? What's going on? So points. Oh, then here again. Okay. Yeah. So back to browser. Refresh. Now it's good. Now let's look at our elements. Correct. You see, we got this polygon element. You see, it's all good. Now, why is it not showing? Possibly because, oh, I know why. Because right now, you see, our polygon, our length is our square has a width of 2, basically. But our canvas is 500. So we don't see it. It's tiny. That is why. So in order to solve that, we can add something called user coordinate. So let's do that. View box. Now view box takes 4 numbers, x and y, and width and height. Okay, xy is the origin on the upper left corner. Now let me go back to the HTML and let me show you something. Okay, let's add a style here so you can see a border of the SVG. So style, box 1, border. Okay, solid thin gray. Okay, now back to the browser, show. Okay, that is our canvas. So we know our image should fall inside it. So now we got a border. We go back to JavaScript and let's see what did we I closed the window by mistake. So many mistakes. So any questions so far? So far so good, guys. Let me know. Okay, so questions. Okay, so we're going back to JavaScript and we are okay, we got a so far so good. Great, thank you, Alan. So we back to JavaScript, refresh again. So right now our cube is too small. So we are trying to solve that. We trying to solve that by adding a user coordinate. So here we tell JavaScript that we tell the browser that from here to here, from the left to the right, instead of it's 500 pixels. However, we want to tell the browser to consider it to be, let's say, 4 instead of 500, and so because our square is only width 2, and the xy is the upper left corner. We are trying to tell the browser what's the coordinate of that point. So we want it to be a negative 2 and negative 2. Okay, so in this case the origin should be in the center. So let's refresh. There it is. We got some kind of thing. We got that's a face. Actually that's not a face. That's the stroke. So what have we done? This is actually not good because okay, so the SVG, let me explain this. So we got this SVG canvas. Okay, the SVG by default from left to right is the x-axis and the vertical is the y-axis, and by default the top left corner is 0 0. So x goes from left to right and y goes from top to down. And you see what so what we are doing, why is it shows like that? Because our face happens to be, we are actually just seeing a line because we are looking at the face edge on. That is why. So let's change to some other face. Let's redefine it. Let's change it to some other face. So let's change it to let's figure out. So 0 0. So that, let me figure out. Okay, so negative 1 1 1. Okay, so from here negative 1 1 1. Okay, then negative 1 negative 1 1. Okay, then negative 1 negative 1 1. Okay, So the z is all just 1. Okay, so let's try that in browser. Let's refresh. Okay, we got something else. Now this is incorrect. We still got something wrong. Now let's say stroke width. Okay. Now because stroke width 0.2. Okay, then back to the browser. Show. Okay, it's better, but it should not be a triangle. Something is wrong here. So 1 1. So 1 1 1 1 1 negative 1 1 negative 1 negative 1. Oh, the last one. So it should be 1 negative 1. That's why. There it is. We got a face of a cube. Okay. Now we are going to rotate this thing, my friends. We are going to rotate this thing in real time. Okay. Now you see, I'm going to show you the fundamentals how to write this. You see, we got one face. Later on, you can add, phase 2, phase 3. When we have time, we'll do that. But now let's do this. But for now, let's try to rotate this thing. So in order to rotate, okay, hold on a second. Let me get this. Well, yeah, perhaps I take a break and let's see what's going on with the comments. So far, it has just manual DOM manipulation stuff, nothing math, graphics specific. No, we got graphics. Well, nothing math, graphics. We got math and we got graphics. Actually, this projection is called parallel projection. It's actually math. It may seem simple because the way we do it, because we are just, it like if you don't explain, it looks like, oh, you just drop z. It's like silly, but it's not silly at all. This is technically it's a projection with a projection point at infinity. Okay, that's what it is. Parallel projection. And anyway, it'll get interesting when we do when we want to do the um, rotation, because that will require a matrix multiplication. Okay, so actually, so let me take a break. So at this point, there are quite a few ways to go. Depends on. So let me ask you guys a question. I'm wondering whether I'm getting hot or not. I guess not so much. So let me ask you guys a question. So we have 3 ways to go. One, I'm going to explain projection, not parallel projection. I'm just going to explain a little bit about projection because that's really interesting. Because when you want the application to be in the end, you don't want parallel projection. Because your eyes in real life, it's not parallel projection. You want perspectivity, because something closer is bigger. Okay, things far away is not. Is smaller. That is projection. Uh, so we, so I'm gonna explain that. Okay, explain projection. So let me know which one you want. Okay, explain projection a bit. Okay, or 2, explain rotation. We are going to do a rotation that is basically matrix multiplication. Okay, but I'm going to explain how do you derive that. Now, okay, explain rotation. Explain how to derive the rotation matrix, or what does matrix multiplication means, because if you haven't studied this before, when you say matrix multiplication, it seems magical. Oh, something just come out right. So I can explain that, or forego those. Just get on with the code as far as we can. So which one? Like which one interests you? That's the key. Which one you are interested the most. Okay, whoever's are still here. So explain projection, or two, explain how to derive the rotation matrix, or continue with the code so you can actually see more JavaScript and stuff. So guys, let me know. Okay, pick a choice. So Bart, are you still watching? Bart, give me a choice. Let's see how long I've been talking. Uh, Live stream video. So Fitch says 3. Okay, we got 17 people. Not too bad. 1 vote for rotation. Okay, so we got the tie. One more. Okay, 3. Wait. So Alan says 1. Explain projection. Now Fitch says 3. Continue with the code. Okay, push out the JavaScript code. And 1 vote for so Emily says rotation. Okay, so we got a tie. Each one got 1 vote. Okay, I'll just do all then. Let's do quickly. We can do that. So projection, it's easy to do. Okay, well, we are not going to do it today, but let me just show you the basics. Stereographic projection, projective illusion. No, that's not what we want. We want okay, so linear algebra. So in this article, I describe the differences between technical drawing and descriptive geometry and projective geometry and linear algebra. You can read it offline, but basically this is what projection is about. Projection is what allows you to have realistic drawings. In before 1800, before 1700, when people draw, like in churches, it's like flat. God, all the people are flat. You don't have realism. But however, this drawing by this guy, Albert Albert Dürer, he's a master. Okay, not this page. Now this guy is a master of illustration. He's a you probably have seen his work. It's fantastic. He's one of the best artists. Okay, so you see, when you look at these drawings, they have realism. Why? It came from projection. Okay, projection is a key. Now, when you look at this window, okay, this window actually also illustrate projection. When you have shadow, shadow is the best example of projection. If you have a flashlight or candle, when you have a sphere or something, you can see the shadow. That's projection. So basically, you have one point, it shoot out straight lines all over. Then the straight lines will touch whatever object, whatever object like a ball or whatever object. Then it will hit the ground. So the point on the object and the point on the ground, that is the point on the ground is a projection of the point on the object. So in the case of a window, the patterns on the window get projected into the wall. So that's projection. That's in principle. Okay. So this, there are many type of projections, but the one we are talking about is called how do you call that? Anyway, it's just called projection. It's the most important projection. It is from projection that gives you realism in drawing. So it may seem trivial to us today, but back in 1500, so there it is, 1471, 71. Most people do not understand it. When they draw, they draw flat, like children's drawing. Flat, everything is flat. They don't understand it. So it takes us something like 1500 years to understand projection. And this guy illustrates projection. So you can see basically from one point to the wall, to the canvas. So here, so the point here, this point is a fixed point. That's kind of the light source. You call that light source. Then you have, this is the object you want to draw. So for every point on the object, you draw a straight line to the light source. Then you have a plane crossing that straight line. So the intersection between the line and that plane is the point you want. Then you get realistic drawing. Okay, so that's about projection. Okay, and today we have CAD software, we have Blender, we have AutoCAD. They are all based on projection. Okay, so that's all projection. Except it's automated. It's done by, how is it done? It's done by matrix multiplication. But that's another thing. Okay, so let's copy that. So let's close that. That's about projection, and that's about that. Projection. So we gotta finish this. Okay, so projection. Then we're gonna talk about, what's the other thing? We're gonna talk about. So okay, wait, hold on a second about projection. So you have seen that. You have seen that. This is projection from one point. Okay. Now, actually, hold on a second. I have another illustration somewhere. I need to show that because perspective drawing. Okay. So here is another example of projection, and this is exactly what we are doing. So you see a cube. That's what we are going to draw, and this plane is our canvas, and this point here, that's a projection point, or the position of the eye. So you can think of that point as a position of your eye. So just like before, for every point on the object, you draw a line to your eye, or the projection point. Then the intersection between that line and the plane should be the point on the canvas. So this plane is called canvas. So that's how you get realistic drawing. Now we are going to do a little bit variation. Now suppose this eye point is moving further and further away. Then apparently what you will see on the canvas will be different, slightly different. Okay, mostly the same but slightly different. If the projection point moves to infinity, like very far away, then that projection is called parallel projection, and that is what we are doing here. So you see, this function, parallel projection, you see, when you do projection, you have a point on three-dimensional space. The output of the function is a point on 2D, so you essentially lose one coordinate. But when you do parallel projection, then the computation is very easy. All you do is drop, you just drop you just drop one of the coordinate. That's it. That's parallel projection. But if you want to do, the normal, the, how do you call this? What's the name? You can look at let's look at Wikipedia, then we'll find the proper name easily. So parallel projection, so there it is, Wikipedia. uh, so parallel projection is a projection of an object in 3D onto a fixed plane, known as projection plane. Blah 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 blah. Orthographic, yeah, it's also known as orthographic projection. But I'm trying central projection. Okay, so the one we are talking about, the projection from a point, is called central projection. But when this point moves too far away, it's called parallel projection because all the projection lines becomes parallel. So parallel projection is most easy to compute. So that's what we did there. Now let's do the derivation of rotation matrix. But first of all, let's just do the rotation matrix so we can actually show the stuff. Let's show the stuff. We gotta show the nice things. That's interesting. Another interesting thing. Okay, I don't know the formula offhand, but let's just copy. Okay, git, because I've written this before. Git. Okay, let's go to where? Let's go to talk show. Let's go to talk show and projection. Polytopes. Polyhedron rotate. Okay, here is the code. Here's the code I've written before. Okay, I'm gonna just show you. Okay, you're gonna see it here. Close that. Close that. Okay, we're gonna put the code here. Let's just draw this first. Then we're gonna talk about. So this rotate x. Okay, so let's talk about this rotate x first. So rotate x is a function that will rotate a bunch of a point around the x-axis by this many degrees. Okay, it rotates counterclockwise. So this here is a formula. Okay, basically it's just sine and cosine, sine and cosine. Then we need to fix the code here because it's incompatible with the way we are doing. So vertices. So vertices is actually just is our phase one. Okay, so vertices is our phase one. Yeah, phase one. Okay. Okay, so let's look at this code. So first of all, we define two constants: cosine something something, sine something something. Then we remember phase one is a bunch of points. We just want to rotate them. So this is the original position, very nice coordinate 1 or -1. Now we want to rotate them by certain degrees. And it should, so what we are doing is we map them. So phase one is a array. We map it, by this function. So here is a function. So this is actually the rotation formula. Okay, so it's easy to understand. I mean, this JavaScript, it's easy to understand, right? So far. So let's, to make sure it works, let's just console log. Let's just print it and see what happens. Console log. So we're gonna rotate x by, let's say, 10 degrees. Okay, we're gonna call that. Then we print our phase one. Let's see what happens. Let's go back to browser. Let's go to the cube. Let's go to the console and let's refresh. Please make it work. No, type error assigned to constant variable. Oh, what idiocy. Phase one should be not constant because we want to change it. Now back to browser, refresh. Yay! Fantastic. Let's see. Now we are talking. What is this? Um, yes, indeed. So again, it's a list of points, and now all the points changed. You see, it's no longer just 1 and -1 because we rotated. Let's try rotate some more. So instead of 10, we say 20 and show it. Okay, let's see what's the value. So the x-axis remain 1 and -1, obviously, because we are rotating around the x-axis, but the others all changed. But let's. So why is it not like the? You see, we are seeing the face. It should be, we should see something like that. Rotate. So okay, so let's continue with this. So oh yeah, because we haven't actually changed the SVG. Yeah, so let's do it next. Let's do it now. Okay, so rotate formula is working. Now we need to um, change the face. Okay, so SVG face we actually want to. So what we do is let's copy it, create it. We'll get back to the derivation in a bit. Let's continue with the code for now. So constant face 1, we start with face 1. Actually, we want rotate first. So we rotate by 20 degrees. Let's say by 30 degrees. Let's say by 45 degrees. Okay. Oops. 45 degrees. Okay. Then we now it's rotated. Now we generate the SVG face. So face 1. Now we project it, and now we generate the code. That's right. So we comment out our previous face, and let's go to the browser, refresh. Okay, rot is not defined. What the hell? Back to the browser, refresh. What the hell? Reference error. Rot x before initialization. Okay, we need to put the functions up. Copy. Okay, put the functions at the top. Okay, let's say here. Back to the browser, refresh. Now it's working because you see you are seeing a face of a square, and we are trying to rotate it around x-axis. So now it's rotated 40 degrees, so you no longer see a square. So now that's done. Let's continue. Okay, let's push on. Let's see how long I've been talking. 1 hour and 7 minutes. Oh God, I got. So projective rotation. So okay, so linear algebra is when I give up on math. Oh, linear algebra is one of the. Have you done calculus? Linear algebra is actually more fun than calculus. Well, it depends on the people, but linear algebra is not hard, so you might give it another shot. It's easier than calculus. Uh, it's not isometric projection. Well, no. Well, isometric projection, that's like gamers. That's their thing. Well, in math, there's just central projection and parallel projection. In math, you don't call it. Isometric projection is rather it's gamers or engineers. They need to draw stuff. So anyway, perspective versus orthogonal view. So again, you have lots of jargons, right? But you need to organize those jargons because a car, what's the difference between a car and a vehicle? A child would not know, but you would know. They are the same thing. Vehicle is just a more academic, generalized name for car. So it's similar in math. So let's so in math you have central projection, which is like how shadow works. Now is if the light ray is far away, like the sun or moon, then it becomes parallel projection. That's what you need to know. That's important. That's how shadow works. Shadow, the shadow from the sun or the shadow from the moon, those are parallel projection. Okay, this is important. But the shadow from a candle or from a spotlight, those are central projection. Because the projection point is close. It's not infinitely far. That's all you need to know. That's the essence of math. Now, the orthogonal view or perspective or isometry projection, those are, derived jargons from these. Okay, so central projection, we are doing parallel projection, which is like the shadow of a sun or moon. And now we are going to, so we successfully rotated. Now let's use JavaScript. Let's create a real-time rotation. Okay, so we are going to add a event. So we are going to say, if user presses up and down arrow keys, we want the browser to detect it. So each time user press the arrow, it will rotate. So user holds down the arrow, it will continue rotating. So let's do that. So what do you have to do? So let's get the box actually needs to the top. Okay, so the box is our div element. So box 1, let's say box 1 add event listener. Okay, add an event in JavaScript. This is how you do in JavaScript. Then the event will be key press. Okay, then so when user press a key, we need to do something. So what we want to do here is rotate it, render it. Okay, so okay, let's do it. Rotate and render. Okay, so write a function, arrow function takes no argument, and we're just going to say rotate around x-axis by 5 degrees. Okay, then we need to write a function to render it. Okay, so basically that's the code. Now we don't have render yet. Actually we already have, but it's not a function, so let's make it a function. So we need to create a render function somewhere here. So let's say constant arrow function render. Now the render will be, delete that, cut that. We have already written all these. Okay, that's our render function. So render function will create a face, it will create a face, then it will append it to the SVG. Okay, so let's do that. So that's what happens. So render will create the SVG face, then append it. Let's go back to browser. Let's just try it. No, I know it won't work because we've got problems. So why is it not working? So console, no error. Amazing. So we got the SVG stuff. We don't have You see, we don't have the polygon. That's why it shows nothing. Why is there's no polygon? Oh, because we wait. So here's the SVG. So this is actually, that's what it's trying to create. So render, create a polygon. So we have created a SVG there. Then when render is called, it creates a polygon and then attach to the SVG thing. Append child SVG face 1 to the SVG element. Then the SVG element is attached to box 1. So why is it not working? Show it. Oh my god, it's not working. Debug time. Linear algebra perspective. Okay, so why is it not working? Check Discord for perspective projection picture. Oh, okay. Let's let's check it out. Discord. Where is it? Real life. No, I don't see projection. Perspective projection picture. Check Discord. Oh, programming. Oh yeah. Well, that's that's not well. That's that's abusing projection to create illusion. That's what that picture is. It's a famous painting. I mean, it's a famous drawing to use to wait. Oh, that's actually accurate. Yeah, yeah. Never mind. I was. I think no. I remember if I recall correctly. This is this picture is trying to abuse projection to create absurdities, if I recall correctly. I may be wrong, but let's go back to what we are doing. So there's a problem. Why does it not show? So we got a SVG element here, and we render. Did anyone call render? Yes, render is called. Oh, that's right, because render is not being called because you have to press a key to render, and we didn't press a key. For example, if we press a key, then it'll work. So let's go back to browser. Let's press up arrow. Up arrow. Wait, the cursor must be here. Let's press up arrow. Wait. Okay, so box 1 key press. Why is it key press? Rotate X. So rotate X rotates the face. Face. You see, the rotate should be below the face. We got everything so wrong there. Okay, now back to browser. Now the code is a mess, but that's what prototype is. Now let's press a key. Let's see. The code is a mess. It's not working, but let's just say, oops, let's just say put render here. Okay, refresh. Okay, so we have, so whenever a key press happens, we want to rotate by 5 degrees and render, but we want to know if it actually detected key press. Okay, so let's put that. Go back here, refresh, go to the console, press some key. So key press is not being detected. So I think the capital P, let's go back to browser, refresh, press a key. No. So what is the, okay, let's cheat. Let's look at my code. Let's see what is the key down. Okay, it's not key press, it's key down. Very annoying JavaScript. Okay, so we got it. Close that. Key down. Okay, back to browser, refresh, key down, press, refresh, press a key. It's not printing anything. It should be console log. Now key down, is key down capital or what? Capital letters or what? No. Oh, document body. Okay, let's do document body, not box one. Okay, document body. Okay, back to the browser, refresh, press a key. Now it's working. So now we are actually seeing rotation here. Success, at least. He's projecting 3D object absurdity to 2D picture. Yeah. So that illustration is it's famous. It's popular. Like when you take drawing classes, they show you this. When they teach you about projection. So anyway, so let's so far successful. Now there is something wrong here though. When you press a key, why is the blue part does not move with it? That's because every time we draw, the last frame is still there. So it's actually drawing multiple face of the cube. So we need to remove it. We need to remove what we've drawn. So let's do it here. Now what I'm doing here is very inefficient because you when you want to rotate a cube, you don't want to redraw everything every frame. But let's just get it to work. You know, you know the basics, know the principles. Then you can think of ways to improve. So what we want to do is to remove the. You see, let me show you what we are doing. So you see this box element, then we have the SVG element, then we have you see these polygon elements. You see we have so many polygon elements because we did not remove the old one. We just draw lots of them. So each time we draw a new one, we want to remove the old one. So how we do that? We do that by just remove children. Okay, so that you can do by dot inner HTML equals to nothing. Okay, that's one way to do it. Refresh. Now press a key. press a key. Now it works. Now let's add another. We are almost done. Okay, 10 more minutes. Let's hope. Then maybe we do the derivation of this matrix multiplication. You are actually not actually seeing the matrix here because it's already multiplied out. But it would be interesting to explain the matrix thing. So anyway, but let's continue to push the code so we actually have something to show. So rotate Y. Let's rotate another. Let's create another rotation around Z-axis. Okay, so let's make it so that when up down arrow is pressed, it rotates around X. When left right arrow is pressed, it rotates around the Z axis. So we got different rotations. Now, okay, so let's do that. We don't need that anymore. Okay, so rotate X, rotate Z. If okay, I don't remember the key, but this is a bit complex, so actually we need to look at key code. Okay, close. So basically we need to detect the arrow key. So this is how you do it. So let's see, let's copy that. Up arrow, so do key press. Okay, so instead, so let's do this. Let's just copy and paste code. Okay, that's what we're gonna do. Do key press. Wait, what's going on? Do key press. Okay. That's right. And here is the do key press. So if it's okay, so if it's up down arrow, we rotate around x-axis. If it's right or left arrow, we rotate around z-axis. Then we render. Okay, that should work. Let's go back to browser. Refresh. Now let's press up arrow. Please. It doesn't work. Coding. So do key press. Why is it? Why is key press not working? Don't tell me that I have to use the other key code thing. Yeah, very annoying. So do key press. Let's do a console log to see if we actually if the code actually run. Refresh. Go to console. Key press. Okay, cannot read property key code of undefined. Oh, okay, so you need to pass a right. You need to pass a event. Okay, so that's K is stand for key. There it is. So we don't need two of them. You just one of them. Back to browser. Refresh. Up arrow, up arrow. There it is. Down arrow. There it is. Right arrow. There it is. Up arrow again. There it is. Fantastic. Now this is now we are. I think we can consider this as done. Now all you have to do now is add the other faces, right? So let's take a break. So let me ask you guys, so should we continue to make it full cube, or should we try to explain the about the matrix multiplication? How do you get the rotation matrix? 1 hour and 30 minutes. So that's that's 90 minutes for today. So what do you guys what you would like to see? Like what you would for yourself? What would you do you prefer? Should we finish to make it a complete cube, and then we can add transparency so it looks nice, or we take 10 minutes, complete the cube. Emily, MTR. What does MTR mean? Matrix. Oh my god, again, disagreement. Which one? We need one more vote. Okay, guys, we got 18 people. Someone else put another vote. It's I don't know if maybe we can do both. I don't know. So let's try to add another face quickly. So okay, so let's see what happens. Now I'm getting more into the math of it. So more math. Okay, more people want to matrix. Okay, so matrix multiplication. I mean so here the question, the problem is the problem is rotation in 3D space. Okay, so you have a point in space. You want to rotate it around x-axis or y-axis or z-axis, any one of these axes. Now, if you want to rotate it around like a oblique axis, then it gets a bit more complicated. But however, any rotation in 3 space can be done by any sequence of just rotating around 2 axes. Okay, so we don't have to worry about complicated rotation around a oblique axis. So for example, let me show you what is. Okay, this is getting complex. I need I need tools, you see. Jesus. So this is xyz axis. Okay, so you can rotate around one of these, or you can rotate around. I'm out of pens. Or you can rotate around some oblique axis. But anyway, the thing that there's a theory. Basically, any rotation around anywhere can be done by a sequence of rotation around these 3 axes. So that's what we're gonna focus on now. So since they are symmetric, so it doesn't matter which one we do, it's basically the same. So we can now just focus on rotating around one single axis. Okay, so basically we want a function. So given a point in 3 space, x, y, z coordinate, you want to get a new coordinate. That's this point rotated around x-axis by alpha degrees, right? So a function, the input is a 3D coordinate, the output is another 3D coordinate. The question now is, how do you compute it? How do you find it? Okay, so, and we already talked about general rotations. It can be reduced to rotation around a single axis. Let's say x-axis, because they are all the same. So let's just focus on x-axis. So now we can actually reduce it further, because we are rotating things all around this axis. So it doesn't matter where we are. The doesn't matter where the point is on the x-axis. It's like the rotation is like a cylinder. It's like a cylinder. So instead of 3 dimension, we can actually now reduce it, like collapse the whole thing into a plane. So it becomes plane rotation. So we just have to think about the plane, because the z the height of the thing, it doesn't change. We are only changing. So if we are rotating a three-dimensional point around the x-axis, you see the 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 x-axis, the x coordinate never changes because they stay the same. It's only the points, the y and z coordinate changes. You see, so therefore we can reduce the rotation further by just thinking about a plane. So let's start over by just thinking about xy, the standard xy plane. So now our problem is to rotate a two-dimensional point around the origin by certain degrees. Okay, we want to derive that. How do you compute? Like, for example, I say I have a point at 2 1. 2 is the x-axis, 1 is the y-axis. I want to rotate it by 40 degrees. What is the new coordinate? That is a problem. Okay, now you see we have reduced three-dimensional rotation to just the planar one. Like, does that make sense? It may be, if this is new to you, it may be overwhelming, but you think about it, it's, rewatch my videos. It's very simple. So now we are talking about two-dimensional plane. We want to figure out how do you rotate a point to another point. What's the formula? Okay, and that involves two-dimensional matrix. So before we have 3D matrix, now we have 2D matrix. We'll get to what matrix means later, but now let's forget about matrix. So we want to find a formula. So what is the formula? um, okay, so makes sense. Okay, so great. So we want to write a function. Basically, normally when you program, you write basically you want to write a function rotation. Okay, 2D. Let's say 2D. So for example, this has nothing to do with our code, but let's just okay. So let's create a new buffer. Let's write it here. So we write a function such that normally in any language. So we xy. So it's like that. Okay. So wait. Xy alpha. Okay, and it needs to equals to something. Something. Okay, that's what we want to do. Okay, so how do you do it? How do you do it? It's very simple. If you Now what you need is trigonometry, basic trigonometry. Then you'll know how to do it because you start simple. Uh, so if you I assume most of you have forgotten trigonometry because most programmers you don't need it. So so I'm explaining the basic trigonometry here. Once you know trigonometry, the whole thing is like trivial. It becomes so easy. So let me see if I can. Uh, I have articles written about it already. Let me see if I can pull it up. So let's go here. Let's go to coordinate transformation. Typically, they call it, mathematician calls it coordinate transformation. but you have not taken trigonometry, have you, or have not? So what's her name? Is she here today? But Ztron Crazy. Ztron Crazy is not here today. She is taking trigonometry, or has she already? So, well, if you want to do math, you should take trigonometry. So it's basic. 3D kernel to add in trick to programming projects. Okay, so how do you do that? So rotation of a point. Okay, so let's explain. So let's go here, translating a vector, rotate a vector. So how do you explain this? So you have to actually, you need to draw. I need to draw. You know, I don't think I can, because you need to start GIMP to draw. Oh, this is so powerful, this tablet. I don't think I have it set up, and but you need to draw triangles, because in order to actually talk about this, otherwise, you know, if we didn't do this, let's see, that'll just be it. If we don't finish this in, you know, 5 minutes or something, then that'll be it. That's it for today. Ah, there's too much problem. Okay, now let's try. So we need to go to GIMP. We need to go to a new one, and we need to go pick a big canvas and say okay. So let's see if I can. Oh, okay, we can kind of draw. So first of all, we need the x-axis. So here's the y-axis. This is too big. Okay, so y x, yeah, kind of works. It's amazing I can actually get this to work. So we have y there, we have x here. Let's say this is our point. Okay, this is a. Okay, now we want to, let's say, how do you do this? Okay, so actually let me show you, this is how we do it. This is a circle. Okay, uh, this is a funky circle. Okay, funky circle, and this is our point a. We want to, let's say, b. Okay, this is our destination, and this is alpha angles. We want to rotate a point a by alpha angles. We want to find the coordinate of b. You know, what is the actual coordinate? So the coordinate of b will be here, this one, b1, and basically b2. You know, so the question is, that's not, it should be 2. The question is, how do you get b1 and b2? So trigonometry, you know, oh god, I'm talking about trigonometry. You need to, find, yeah, so you need to find, so we have, so this is r, this is this is the hypotenuse. So anyway, we start with a point A. We want to rotate by alpha angles. That's all we know. We don't know anything else. So we should end up at some point B. You know, we want to find the coordinate. How do you do it? Now, if you assume, let's assume alpha is small. Let's say 30 degrees, 40 degrees, something like that. So it looks like that. So, let's use this graph, for example, to do derivation. Then we can extend it later. So this r is the radius of the circle, because that's basically the length of a. So a has the coordinate of r 0 basically, and we know alpha is 40 degrees. Okay, alpha equals to 40 degrees, let's say. Okay, so we know this length, and we know the angle, and what else? We need to derive a formula for rotation. A rotated by that. I don't, well, so we know, I need to explain a lot, you know, the sine cosine formulas. So sine x equals to y over r, cosine alpha, it's some angle, okay, equals to x over r. Cosine start with 1, so when it's 0, yeah, okay, so that's sine cosine. Well, you see, I need to explain that, but but uh, so anyway, let me try to figure this out. So yeah, there you have it. Actually, we already know the answer. So you see, now I'm not going to explain this y sine alpha equals to y over r. You need to study trigonometry, but anyway, we have this formula. So alpha is known. Alpha is known here. Okay, so sine alpha, we know that value, and r is known. R is the length of our point. Given a point, you can find the length by, again, trigonometry. Okay, so r is known, sine is known. So y becomes r times sine alpha. So now you can know the there. So the y equals to r times sine alpha. And x, similarly, we also know the x here. So here is x. Okay, similarly, it's already bad. Actually, that's not x, that's y. This length is x. Okay, so we know y and we also know x. X equals to r cosine alpha. Okay, we know this. So the beta. Okay, so this is b1 b2. Actually, this is b2, this is by bx. That's a coordinate. Okay, that's actually so we actually, in fact, derived the formula to compute the rotation of that, kind of. This is a very lousy job, but maybe it gives you some ideas. So does that make sense at all? But I think that's it for today. Um, okay, so yeah, okay, so thank you guys for coming. And that's it. So you can simply simplify it to make it easier. So I think I should stop now. So what? 150 minutes. Yeah, that's it for today. Thank you for guys for coming, and that's it. Bye, guys. The trick. I don't know if I explain. Well, actually, it's not hard to explain. The sine alpha equals to this. This is basically the definition of sine. But anyway, so look up, guys. This is a great opportunity. What I'm what I'm doing here is equal to, is like equals to a week's course It's like a half semester in college. Okay, hey, is this one crazy? Okay, because the professor will go into details, but this is the gist. And so I hope you get some ideas. So then now you go to look Wikipedia, like how rotation matrix, then you start to get it. Now we haven't started to talk about matrix yet. Like so far it's like what where does it came from? Like what the heck? But right now we do have a formula for rotation. A matrix is basically a format. You turn this formula into a format, so things looks neat. That's all basically. The formula is the key. That's the heart of the thing. Bye guys. So I'm gonna shut down. I'm closing down, and see you next time. Let's see my code. So our code is still working, and our code is fantastic. It actually works. Where is our code? Yeah, so we can rotate it by both axes. You see, we can now we can this